Okay, let's look at this example 4C3. So a tug having mass of m is towing a coal barge with the mass mb with the speed va1. So at the beginning, they both have the speed va1. And during a short period of time, delta t, when the engine of the tug are turned off, the stern wrench takes in towing cable at the rate of VB/A. So the first part of this question, we need to determine the speed of the tug during this period of time. And the second part of this problem is we need to determine the average value of the tension in the towing cable during the time delta t. Okay, now let's look at part A. We need to find the speed of the tug during the period of time delta t. So in order to do that, we first need to look at both A and B as a system. Then we can draw the free body diagram for the whole system. Treat them as a system. You will have weight force WA and normal force NA, weight force WB, normal force MB, and make sure you label them as vector. And you probably noticed I didn't show the tension force in between A and B. That is because the tension force is an internal force, and when I take A and B as a system. So then I can set up my coordinate system I and J. Since both boats are moving to the left, so it'll be easier to set my I towards to the right left, and the J is on the vertical direction. If you look at this free body diagram, and you probably realize that all the forces on J direction it's 0, right? And all the forces on I direction is 0. There's no forces on I direction. And so since we're interested in the velocity on I direction, so we will apply the impulse momentum equation on I direction. And the impulse momentum equation, we need sum of the forces and integral sum of the forces delta t. That's on the left side of the equation. On the right hand of the equation, you need to have the change of momentum, which is sum of all the forces times V2 minus sum of all the masses times V1. Here's one. Then since we know there's no forces on I direction, so the left term becomes 0, right? And the left term, since we have two masses A and B, so we have sum of the forces both MA times VA2 plus MB times VB2 minus MA VA1 plus MB VB1. So this is the first equation we get from the impulse momentum equation. And then the second equation we can get this from this problem is both boats A and B are moving at the same speed or velocity at the beginning before towing. So VA1 equals VB1. They both equals to VA1I. So that's the second equation we can have. The third equation is from the wrench. So the wrench is running at the speed velocity of VB/A. From the kinematics, we learned the relative velocity can be written as VB minus VA, right? And we can write VB in terms of VA and VB/A. So VB equals VAI plus VB/AI. That will give us the third equation. Then we can plug both equation 2 and equation 3 into equation 1. And so I plugged equation 3. That's the expression for VB2. And also I replaced, like the equation 2, replace both VA1, VB1 equals to VA1. Now we have this new expression. If you look into this line equation, VA2 is the unknown variable we try to solve, right? So we have two terms have VA2. So we want to put them together and throw everything else into the other side of the equation. Then after arrangement, we get VA2 times MA plus MB equals MA VA1 plus MB VA1 minus MB VB slash A. So everything is pretty clear now. VA1 is something we try to solve. And on the other hand of equation, VA1 VB slash A are the givens. And we know the masses from both boats. So we can throw MA plus MB to the other side of equation. And you should end up with the expression for VA2. And you can keep simplify the expression for VA2 by writing all the vectors in terms of I and j's, right? Then you will find out all the velocities VA1 and VB slash A are on I direction, so you can pull the unit vector I to the outside of the equation. Then you end up with the expression for VA2. And VA2 equals MA VA1 plus MB VA1 minus MB VB slash A over MA plus MB I direction. So that's the answer you're looking for.